Hello, in the previous video we have talked about voltages. So in this video we'll be talking about electric current. So we were saying that the battery is kind of like a water pump and the charges are kind of like water. So the electric current will be kind of like the water current here. If you insert a flow meter into the water current, then you can measure the rate of flow of water, the amount of water flowing past every section per unit time. So similarly, in an electrical circuit, we can insert an ammeter, and the ammeter will be measuring the electric current, the amount of charges flowing through per unit time. So the electric current is the rate of flow of charges, is measured in ampere, and 1 ampere is 1 coulomb per second. Let's imagine a tungsten filament. So in a tungsten filament, we have all these mobile electrons, the so-called cloud of electrons, buzzing around the positively charged metal lattice. So these electrons will be moving at random directions, but as they collide with the lattice, they will rebound. So all of them will be doing this jiggling kind of things. So all these electrons will be moving around at very high speed, undergoing collisions with the lattice. So the path taken by this electron could look like this. Now the thing is, because everything is random, after a certain amount of time, every electron is equally likely to have gone right or gone left. So the net of flow of charges will be 0. So there's no electric current. To have an electric current, you need to apply an electric field. So if there's a leftward external electric field, then all the electrons will be experiencing a rightward electric force. Then on top of this random direction, you have a steady drift of electrons rightward. So the path taken by this electron could look something like this. So it keeps colliding, but there's this electric field that's drawing it steadily rightward. Now let's imagine a line here, and let's imagine that 10 to the power of 19 electrons cross this line every second. That will imply negative 1.6 coulombs of charges crossing this line per second. Remember, each electron carries a charge of 1.6 times 10 to the power of negative 19. So 10 to the power of 19 electrons has a total charge of negative 1.6 coulomb. So what's the magnitude of the current we're talking about? 1.6 amps leftward. Not rightward, man. The electrons are drifting rightward, right? That's because by convention, we define the conventional current to be the net flow of positive charges. Now, some students are very uncomfortable with this. They say, but then we now know that the current is carried by electrons, right? So it's a mistake, right? To define conventional currents to be the net flow of positive charges. But not quite, you know. For example, in an electrolyte, the current is actually carried by both positive ions and negative ions. So you have positive ions going this way and negative ions going this way. The current by convention will be defined as this way, rightward. In fact, to calculate the total current, you have to sum up the flow of positive ions rightward and the flow of negative ions leftward. There's also something called a semiconductor. In a semiconductor, the current is also carried by both negatively charged electrons and positively charged holes. In fact, there's something called a p-type semiconductor, and in a p-type semiconductor, the current is almost totally carried by holes. Now, the A-level syllabus doesn't need you to know about the electrolytes and semiconductors, but I'm bringing this up just to inform you that currents carried by positive charges is just as common as currents carried by negative charges. So really, there's no need to redefine the direction of conventional current. In fact, we should count ourselves lucky that 6 coulombs per second flowing rightward has the exact same effect as negative 6 coulombs flowing leftward. So if you were to use an ammeter to measure this current and to measure this current, the ammeter will measure the exact same thing, same magnitude and same direction. So when somebody tells you that there's a conventional current going rightward, you actually don't have to ask, oh, is the actual situation like this or like this? It doesn't matter at all because both will produce the same effect. Okay, now we want to talk about drift velocity. So if you have electrons drifting rightward with a drift velocity of v, there's a current I going leftward, right? We want to know how is I related to the drift velocity v. So let's consider a cylindrical conductor with these mobile electrons drifting rightward with drift velocity v. Let's consider a time duration delta t. In time duration delta t, every single electron will have drifted rightward a distance of v delta t. Now, if the cross-sectional area of this cylinder is A, then we can talk about this volume here, this cylindrical volume in purple. That volume will be given by A times V delta T, right? This area times this length is this purple volume here. Now, what's so special about this purple volume? Well, it's because all the electrons in this purple area would have crossed this cross-sectional area in time duration delta t, because the one that was here would have traveled until here, the one that was here would have traveled until here, and even the one that's here, that's v delta t away from here, would have arrived here. So in time duration delta t, all the electrons contained in this volume would have crossed the line here. Now, how many electrons are found in this cylindrical volume? Well, that number n can be written as n times v, yeah? So small n represents the number of electrons per unit volume, right? So you take the number of electrons per unit volume times the volume, you get the number of electrons. Now we are ready to write down the expression for current. So current is just the rate of flow of charges, right? So we have this amount of charges crossing this section in duration time delta t. Now notice I have to multiply the charge of an electron here, because this is the number of electrons. I have to multiply it with the charge of each electron to get the total charge. So we end up with this expression here. I is equals to NAVE. Now in general, the currents need not be carried by electrons. It can be by any mobile charge carrier. So in general, we say that I is equals to NAVQ. So N is the charge carrier density, it's the number of charge carriers per unit volume. Q will be the charge of each mobile charge carrier. Alright, that's all. Ta-ta!